The speed of light. In the vast expanse of the cosmos, there exists a speed limit that no object, no signal, and no piece of information can exceed. This is the speed of light. 299,792 kilometers per second, or about 186,000 miles every second. To put that into perspective, in just 1 second, light could travel from Earth to the Moon almost 400 times. In the blink of an eye, it could circle Earth more than 7 times. It is the ultimate speed limit built into the fabric of the universe itself, not a human-made rule, not a challenge to overcome, but a fundamental law of nature. Even in the earliest instance of the universe, when particles were colliding with unimaginable energies, nothing exceeded this limit. It's written into the mathematics of reality itself. The speed of light is more than just a number. It is deeply woven into the equations that describe existence. Einstein's theory of special relativity revealed that, as an object approaches this cosmic speed limit, strange and profound effects occur. Time slows down for the traveler, lengths contract in the direction of motion, and the energy required to accelerate further grows without bound. The equation E equals mc squared, perhaps the most famous in all of science, tells us that energy and mass are two forms of the same thing, and as speed increases, the kinetic energy adds to the object's effective mass. Push harder, and the mass increases, requiring more energy in an endless cycle. Reaching the speed of light itself would demand infinite energy, a feat beyond the reach of any finite civilization. Photons, the particles of light, move at this speed because they have no rest mass. For them, time effectively does not pass. From a photon's own perspective, if it could have one, the moment of its creation and the moment it is absorbed would be the same instant. Everything else in the universe, whether it's a spaceship, a proton, or even the fastest subatomic particle we can produce in accelerators, must move slower. The speed of light also defines the maximum speed for causality, the fastest rate at which causes can lead to effects, and at which information can spread. If the sun suddenly vanished, Earth would not instantly drift away. We would continue orbiting for 8 minutes and 20 seconds, the time it takes for both light and the change in the sun's gravitational field to reach us. This delay is not due to any inefficiency, but because the structure of space-time itself enforces it. Even gravity, which we often imagine as an instantaneous pull, moves at the speed of light. When black holes merge in distant galaxies, they send ripples through space-time, gravitational waves, which travel to Earth at exactly this same universal limit. The speed of light, then, is not just a number, it is the heartbeat of the cosmos, dictating the pace at which reality unfolds. The cosmic horizon. Because light has a finite speed, and the universe has a finite age, about 13.8 billion years, there is a limit to how far we can see. This boundary is called the cosmic horizon, the edge of the observable universe. It is not a wall, not a place you could ever travel to, but rather a distance beyond which the light of events has simply not had time to reach us. Due to the expansion of the universe, this horizon lies farther away than you might expect. The current observable universe is about 93 billion light-years across, meaning we can, in principle, receive light from objects as far as 46.5 billion light-years away in any direction. That's because space itself has been stretching over time, carrying galaxies with it. Light that was emitted billions of years ago has been traveling toward us while the space in between expanded. But there's a deeper consequence. The expansion of space means that some regions are receding from us faster than light, not because they are moving through space faster than this limit, but because the space itself between us is stretching so quickly. In those cases, any light they emit will never overcome the increasing distance. We will never see them, no matter how long we wait. This cosmic horizon is in a sense the edge of our knowable reality. Everything beyond it is hidden from us forever. There could be galaxies, clusters, and unimaginable cosmic structures out there, but they are beyond the reach of observation. For all practical purposes, they may as well be in a separate universe. Cosmologists sometimes imagine the universe as an infinite plane, with our observable region as a tiny circle drawn around us. Beyond that circle, the plane continues, perhaps infinitely, perhaps curving back on itself, perhaps even containing regions with entirely different physical constants. We will never know, because light, our only messenger from the distant past, cannot cross that gap. Time and relativity. Einstein's relativity revealed a truth that rewrote physics. Time is not absolute. It is linked to motion and to gravity, bending and stretching depending on where you are and how you move. If you travel close to the speed of light, time slows for you compared to someone who stays still. This is not a trick of perception, it is a physical reality. Atomic clocks carried on jets or satellites tick at different rates than identical clocks on Earth, and experiments have measured this difference with extraordinary precision. Gravity, too, warps time. Near a massive object like a black hole, time runs more slowly relative to regions farther away. This effect has been confirmed in laboratories, where atomic clocks placed just a few centimeters apart tick at slightly different speeds because of Earth's gravity. The combination of space and time into a single framework, space-time, means that when you move quickly through space, you move more slowly through time. The speed of light acts as the ultimate conversion factor between them, binding them together. Near the ultimate cosmic limits, near light speed or near the edge of a black hole, time dilation becomes extreme. To the traveler, their own time feels normal, but from the outside, their clock appears to slow to a crawl. If you could orbit just above the event horizon of a black hole and then return, you might find that while only hours passed for you, centuries had gone by for everyone else.
Black holes are the most extreme expression of the limits set by relativity. Formed when massive stars collapse under their own gravity, they compress matter to densities so high that space-time curves back on itself. The boundary beyond which nothing can escape, not even light, is the event horizon. From the outside, anything that falls in appears to slow down as it approaches the horizon, its light stretched to redder and redder wavelengths until it fades entirely. But from the falling object's perspective, it crosses the horizon without noticing anything special, continuing inevitably toward the singularity at the center. The singularity is where our known physics breaks down. General relativity predicts infinite density and zero volume, conditions that make no sense in quantum theory. This is why black holes are not just astrophysical objects, but also theoretical laboratories for probing the deepest laws of nature. Hawking radiation, proposed by Stephen Hawking in 1974, suggests that black holes slowly leak energy due to quantum effects near the event horizon. Over unimaginable timescales, far longer than the current age of the universe, they could evaporate entirely. But whether the information about everything they swallowed is lost forever remains one of the greatest puzzles in modern physics, the black hole information paradox. Entropy and the arrow of time. Another ultimate limit comes from the second law of thermodynamics, which tells us that entropy, a measure of disorder, in a closed system can never decrease. Over time, the universe evolves from states of lower entropy to higher entropy. This is why time has a direction, why the past feels different from the future. You can remember yesterday, but not tomorrow. You can mix cream into coffee, but not unmix it. Stars shine by converting ordered nuclear fuel into heat and light, which spread into space and increase the overall entropy. In the early universe, matter and energy were in a much more ordered state. Over billions of years, stars formed, burned their fuel, and died, leaving behind a cosmos that is slowly running down. This gradual increase in entropy sets the stage for the universe's long-term fate. The heat death and the far future. If the expansion of the universe continues forever and dark energy remains constant, the cosmos will face a future in which usable energy becomes ever scarcer. Stars will exhaust their fuel and die. New star formation will cease. White dwarfs, neutron stars, and black holes will dominate the night sky. Over trillions of years, even these remnants will cool to near absolute zero. Black holes will evaporate through Hawking radiation, releasing their last photons into an already cold and dark universe. Eventually, all that will remain is a thin gas of subatomic particles drifting through an ever-expanding void. This is the heat death, a state of maximum entropy where no energy gradients exist to power processes or life.
The Planck scale. Physics also imposes a lower limit on scale, the Planck length of 1.6 times 10 to the negative 35th meters. Below this size, our concept of space and distance may lose meaning entirely. The Planck time, 5.39 times 10 to the negative 44th seconds, is similarly the smallest meaningful unit of time. Anything smaller lies beyond our current theories. This is the realm where quantum mechanics and gravity must merge into a unified theory, something we have yet to discover. It's possible that at the Planck scale, space-time itself is made of discrete units, like pixels in a cosmic screen, or is replaced by something even stranger, like vibrating strings or loops. The uncertainty principle. On the quantum scale, Werner Heisenberg's uncertainty principle defines another limit. You cannot know both a particle's exact position and its exact momentum at the same time. The more precisely you measure one, the less precisely you can know the other. This is not a flaw in our instruments, but a property of nature. Particles exist not as definite points, but as probability clouds, their exact properties crystallizing only when measured. This uncertainty lies at the heart of quantum mechanics and shapes phenomena from atomic stability to the behavior of stars. The expanding universe and the cosmic horizon. The expansion of the universe means that some galaxies are already beyond our reach forever. Even if we could travel at nearly the speed of light, space itself would carry them away faster than we could chase them. Our observable universe is just a small fraction of the whole, perhaps an infinitesimal one. Beyond our cosmic horizon lies the unobservable, perhaps infinite reality that we will never touch. Why these limits matter. The speed of light, the cosmic horizon, relativity, entropy, the Planck scale, and quantum uncertainty are not just restrictions. They are the framework of existence. They define the possible. They give shape to time, space, and the evolution of the cosmos. They ensure that the universe is not chaotic, but ordered by deep, unbreakable laws. Within these limits, galaxies form, stars shine, life emerges, and minds ponder the very boundaries of reality. We may never break these limits, but by understanding them, we glimpse the true structure of the cosmos and our place within it.